What if reality itself is built from a seething, turbulent foam? This is not science fiction, but a serious idea in theoretical physics called quantum foam. We are about to journey through 30 incredible theories that attempt to explain this chaotic foundation of the cosmos. By the end, you will understand how this single concept could redefine everything from the nature of time to the fate of our universe. We will explore how this foam might be the source of dark energy and whether it holds the key to uniting gravity with the quantum world. What part of this hidden reality most makes you question what you think you know? John Archibald Wheeler saw a universe of chaos beneath the calm surface. In 1955, this visionary physicist proposed that the very fabric of spacetime is not smooth and continuous. Instead, at the smallest possible scales, it is a turbulent sea of fluctuating structures. He called these entities geons, a name blending gravitational and electromagnetic. Picture the energy of the vacuum itself, seething with uncertainty. The rules of the quantum world tell us that empty space is never truly empty. Particles and their antimatter partners flicker in and out of existence in a frantic dance. Wheeler realized this same uncertainty must apply to the geometry of spacetime itself. Tiny, fleeting bubbles of distortion would constantly form and vanish. Each one is a miniature whirlpool in the fabric of reality, a tiny knot of gravity born from the void. This is the quantum foam. It is a radical departure from the universe described by Einstein, where space and time form a serene and unwavering stage. Wheeler's foam is the stage itself, roiling and bubbling. This foundational idea set the stage for every theory that followed, forcing physicists to ask a profound question. What if reality is fundamentally grainy, a digital projection on a screen we cannot see? This turbulent foam might not be made of spacetime at all, but of something far more fluid. A radical idea suggests the vacuum of space is not a void but a quantum superfluid, a perfect liquid with zero viscosity. In this model, the entire cosmos is submerged in an invisible, frictionless medium. The quantum foam we perceive is simply the churning of this fluid, the tiny vortices and excitations that naturally arise from its quantum dynamics. Think of a perfectly still cup of superfluid helium. On the surface, it appears calm, but peer closer, and you would see a microscopic storm of activity, with tiny whirlpools constantly forming and collapsing. Our universe may be the same. The apparent emptiness of space could be this superfluid state, and the fleeting bubbles of the quantum foam are the miniature tornadoes spinning within it. This perspective offers a stunningly elegant solution to two of cosmology's greatest puzzles. Dark matter, that mysterious substance holding galaxies together, might not be a cloud of unknown particles. It could be the gravitational pull of the superfluid's denser regions, like currents in a cosmic ocean. And dark energy, the force accelerating the expansion of the universe, might simply be the fluid's inherent pressure, a gentle push from the vacuum itself. Physicists are already testing this in laboratories using Bose-Einstein condensates, exotic states of matter cooled to near absolute zero that behave as quantum superfluids. By studying the bizarre behavior of these condensates, they can create simulations of spacetime itself, watching how microscopic structures form and interact. This gives us a tangible, experimental window into the quantum foam, suggesting that the fabric of reality might flow more than it fractures. This foam might not even be three-dimensional at all. The holographic principle proposes a truly mind-bending idea. All the information that makes up our seemingly solid universe, every star, every person, every atom, could be encoded on a distant two-dimensional surface. Our reality, with all its depth and volume, is merely a projection, a hologram. The chaotic structure of the quantum foam is where we see this cosmic code breaking down. Each of those Planck scale fluctuations, those tiny bubbles of distortion, could be a single pixel in this grand projection. They are the fundamental bits of information, the ones and zeros that construct everything we experience. This is the graininess of reality rendered in its most literal form. The universe is not infinitely detailed. It has a maximum resolution, and the quantum foam is the visual static you see when you zoom in too far. This idea creates a stunning bridge between the worlds of gravity and quantum mechanics. In the holographic view, gravity is not a fundamental force like the others. It emerges from the way information is entangled and processed on that two-dimensional boundary. The quantum foam, then, is the turbulent interface where this information is translated into the three-dimensional world we inhabit. It is the engine of reality, churning out space and time from a sea of pure data. We are living inside a computation, and the foam is its most basic processing noise. But what if spacetime itself is built from tiny, woven threads of gravity? Loop quantum gravity offers this very picture, proposing that the fabric of reality is not a smooth continuum but a vast, evolving web. This web is made of one-dimensional loops, intersecting and linking together to form a structure called a spin network. Each individual node and link in this cosmic net carries a specific quantized value. This means that area and volume themselves cannot be divided infinitely. They come in tiny, discrete packets, the smallest possible units of space. This is the genesis of the quantum foam, a natural consequence of space being woven from finite, fundamental threads. The foam is not a chaotic mess in this view, but a highly structured, granular substance. Now, consider how this network changes over time. The history of its transformations, the way these loops reconnect and evolve, is described by a structure called a spin foam. Picture a complex, multi-layered honeycomb, where each cell represents a quantum of spacetime, and the entire, bubbling structure charts the passage of reality itself. This spin foam is the precise mathematical description of the quantum foam, a framework where the universe's evolution is a sequence of discrete steps. This stands in stark contrast to string theory's approach. While string theory proposes that the fundamental objects are tiny, vibrating strings existing within a pre-existing spacetime, loop quantum gravity builds spacetime itself from the ground up. It does not assume a stage for physics to play out on. It weaves the stage from the quantum relationships between its loops. One theory adds actors to a stage. The other claims the stage and the actors are made from the same fundamental material. This offers a profoundly different vision of the foam, not as a turbulent sea, but as the very weave of a cosmic tapestry, forever being knitted and re-knitted into existence. Yet another approach weaves the fabric of reality not from loops, but from vibrating strands of energy. String theory proposes a radical solution to the foam's chaos. It suggests the most fundamental entities in the universe are not zero-dimensional points, but incredibly tiny, one-dimensional strings. Their different vibrational patterns, like the notes on a violin string, give rise to every particle and force we observe. This simple shift from a dot to a line has a profound consequence for the quantum foam. A point particle can occupy an infinitely small location, leading to the wild, infinite fluctuations in spacetime that create a violently turbulent foam. But a string is smeared. It has a finite length, which acts as a natural buffer against that extreme violence. The string's gentle oscillations smooth out the worst of the foam's frenzy, replacing a stormy sea with a more controlled, rippling landscape. This smoothing effect relies on a truly strange prediction: the existence of extraspatial dimensions. We experience only 3 dimensions of space and 1 of time, but string theory requires more for its mathematical consistency. These extra dimensions are compactified, curled up into shapes so tiny we cannot perceive them. The precise way these dimensions are folded determines the properties of the strings vibrating within them, and by extension, the very nature of the quantum foam we infer. In some configurations, the foam might be almost tranquil, while in others, it could remain a bubbling cauldron of activity. The foam is not eliminated, but its character is entirely dictated by the hidden geometry of the cosmos. This framework turns the universe into a symphony where the fundamental notes are not particles, but the resonant vibrations of strings playing out across a stage with many more curtains than we can see. There is another path that builds reality from the ground up, one tiny triangle at a time. The approach of causal dynamical triangulations begins with an almost childlike simplicity. It proposes that the entire universe can be constructed from the most basic geometric shapes, tiny triangular blocks of spacetime. Each one is a fundamental building block, a quantum of geometry with a fixed, simple form. These triangles are then connected to one another, following a strict rule of cause and effect that ensures time only flows forward. This rule of causality is the secret ingredient. Without it, the triangles would connect in every possible chaotic way, creating a jumbled, fractal mess of infinite dimensions. But when causality is enforced, something remarkable happens in computer simulations. Billions upon billions of these tiny triangles, when allowed to dynamically connect and interact, do not remain in a chaotic foam. They spontaneously organize. They undergo a dramatic phase transition, like water freezing into ice. From a seething fractal soup, a smooth, 4-dimensional universe crystallizes. We are not talking about 3 dimensions of space. We are talking about the 4-dimensional spacetime we actually live in, complete with the familiar arrow of time. This is a profound revelation. The smooth, classical world we experience is not a given. It is an emergent property, a collective effect that arises from the collective behavior of an unimaginable number of tiny, quantum building blocks. Our reality is a stable phase of the universe, one possible state that emerged from a vast ocean of quantum possibilities. This tells us that the foam is not our permanent reality, but the raw material from which our stable cosmos condensed. The reason we do not perceive this underlying graininess is the same reason we see a smooth sheet of ice, and not a trillion individual water molecules. Our scale is too large, our perception too coarse. We are living in the emergent calm, a gentle valley in a landscape of quantum chaos. This brings us to a profound puzzle at the heart of the foam. If reality is fundamentally a churning, timeless sea of quantum events, then where does our experience of time come from? The smooth, relentless flow from past to future seems completely alien to the chaotic, directionless foam. Some physicists propose that time is not a fundamental ingredient of the universe. It is an illusion, a story that emerges from the way these countless quantum events relate to one another. Think of a movie. The film itself is just a collection of individual frames, each one static and complete. There is no movement inherent in any single frame. But when you project them in a specific sequence, your brain perceives a continuous flow of action, a story unfolding. our reality might be the same. The quantum foam is the entire film reel, a vast collection of frozen snapshots of spacetime. Our conscious experience, our feeling of time passing, is the projector light, illuminating one correlated event after another. The arrow of time, the reason we remember the past but not the future, could simply be a consequence of the way these quantum states become increasingly entangled and correlated. It is a story written by increasing complexity, not a river flowing in one direction. This challenges our most basic understanding of cause and effect. In a timeless foam, does one event truly cause another, or are they just linked in a vast, static web of relationships? The flow of time, the feeling of a present moment slipping into the past, might be the most convincing and persistent illusion generated by the quantum foam's endless dance. This single discrepancy is so immense it threatens to unravel our entire understanding of the quantum world. The energy density of empty space, driven by the frantic fluctuations of the quantum foam, should be enormous. Physicists can calculate its expected value based on the energy of every virtual particle pair flickering in and out of existence. The result is a number so catastrophically large it defies comprehension. It suggests a vacuum energy density of around 123 orders of magnitude greater than what we actually observe. To put that in perspective, it is the difference between the energy contained in a single drop of water and the energy contained in all the oceans of every planet in the observable universe. This is the cosmological constant problem, and it is widely regarded as the most embarrassing failure of modern theoretical physics. Our best theories predict a universe that should have torn itself apart in a violent expansion within the first fraction of a second of the Big Bang. Yet here we are in a cosmos that is, by comparison, gently and slowly accelerating. So what cancels out almost all of this vacuum energy, leaving behind the tiny whisper we call dark energy? One compelling idea is a cancellation mechanism, a kind of cosmic symmetry. Perhaps for every type of particle that contributes a positive energy to the vacuum, there exists a supersymmetric partner, a sparticle, that contributes an equal but negative energy. In a perfectly balanced universe, these contributions would add up to zero, a perfect cancellation. The problem is, we have not found any of these sparticles in our particle colliders. If they exist, this symmetry must be broken, meaning the cancellation is almost, but not quite, perfect, leaving behind the tiny residual we observe as dark energy. Another theory suggests the vacuum energy is not a fixed number, but a dynamical field that can relax over time. Imagine the universe as a vast, complex landscape of hills and valleys, with each valley representing a possible vacuum state with a different energy level. In the fiery beginning, the universe was perched high on a steep hill with a colossal vacuum energy. But over eons, it has slowly rolled down, settling into a valley that is almost, but not exactly, at zero. We are living in the aftermath of that long relaxation, experiencing the last faint echo of that initial cosmic inflation. The foam's violent energy has mostly drained away, leaving only the barest ripple, which is still enough to push the galaxies apart. This problem forces us to confront a humbling possibility. Perhaps our understanding of the quantum vacuum is fundamentally flawed, or there is a deep principle of nature we have not yet discovered that naturally forces the cosmological constant to be nearly zero. Solving this puzzle is not just about fixing a calculation. It is about finding the missing piece that will connect the furious microcosm of the foam to the serene macrocosm of our expanding universe. The immense energy of the quantum vacuum presents a paradox. But what if the solution has been hiding in plain sight all along? That faint, repulsive force we call dark energy might not be a separate entity at all. It could be the direct manifestation of the quantum foam's own restless energy, finally making its presence known on the grandest of scales. This theory suggests that the foam is not static. Its very structure evolves as the universe expands and cools. In the dense, hot early universe, the foam's microscopic bubbles were constantly colliding and interacting, their energy largely canceling out or remaining confined. But as space stretched over billions of years, the foam's texture changed. The bubbles had more room to fluctuate, and their collective behavior began to exert a new kind of influence. Think of it like a pot of water coming to a boil. At first, the tiny bubbles form and collapse at the bottom. But as the water heats up and expands, those bubbles grow, combine, and create a steady pressure that pushes upward. The expanding cosmos might have allowed the quantum foam to reach a similar tipping point, where its innate energy transformed into a smooth, pervasive pressure permeating all of space. This pressure is negative, a concept that feels counterintuitive but is crucial. We are used to positive pressure, like in a balloon, where pushing on the walls makes it expand. Negative pressure is the opposite. It is a tension, like a stretched rubber band wanting to snap back. But in the strange world of general relativity, a universal negative pressure does not cause collapse, it causes repulsion. It makes empty space want to expand, and it makes that expansion accelerate. The quantum foam, with its frantic creation and annihilation of virtual particles, naturally generates this kind of negative pressure. Each fleeting bubble is a tiny region where the energy density of the vacuum is in a state of tension. And when you add up all these microscopic tensions across the entire cosmos, you get a colossal push. This offers an elegant solution to the dark energy puzzle. We are not searching for an exotic new field or particle. We are simply witnessing the large-scale, cumulative effect of the foam's fundamental nature. The accelerating universe is not a mystery. It is the quantum foam, at last, stretching its legs and asserting its dominance over the cosmic stage. The foam's influence might not stop with dark energy. For decades, astronomers have been chasing a ghost, a substance we call dark matter, whose gravitational pull is the only reason galaxies hold together at all. But what if this cosmic phantom is not a cloud of exotic particles? What if it is another side effect of the turbulent quantum foam? This theory suggests that the foam is not perfectly uniform. Its microscopic bubbles and fluctuations could create tiny variations in the density of spacetime itself. These are not variations in matter, but in the very fabric that matter sits within. On the smallest scales, these variations are minuscule and fleeting. But when you zoom out to the scale of an entire galaxy, their collective gravitational effect could be immense. Imagine running your hand over a sheet of sandpaper. To your fingertips, it feels rough and uneven. But if you were the size of an ant, each tiny grain of sand would feel like a significant hill or valley, altering your path. In this analogy, the quantum foam is the sandpaper. Its microscopic roughness warps the geometry of space on a local level. A star or a cloud of gas traveling through this region does not follow a perfectly smooth trajectory as predicted by Newton or Einstein. Its path is subtly altered by the foam's gravitational texture. From our distant vantage point, we cannot see the sandpaper's grain. We only see that stars on the outer edges of galaxies are moving too fast, as if being pulled by the gravity of some invisible matter. We give that missing pull a name, dark matter, but the matter itself may not be missing. The extra gravity could be an emergent property of the foam's lumpy, quantum structure. This idea would completely transform the search for dark matter. Instead of building ever more sensitive detectors deep underground to catch a hypothetical particle, we would need to look for subtle signatures in the fabric of spacetime itself. We would be searching for the gravitational fingerprint of the foam. If this theory is correct, then dark matter is not a thing to be found, but a behavior of space to be understood. It means the universe is not filled with an invisible substance, but is itself fundamentally textured, and that texture has weight. The violent churn of the quantum foam might hold the key to one of physics' most famous losses. When anything crosses the event horizon of a black hole, it seems to be lost forever, its information irretrievably erased from our universe. This violates a core rule of quantum mechanics, which states that information can never be truly destroyed. This is the black hole information paradox, and the solution may lie in the foamy structure of spacetime itself. At the very boundary of a black hole, the event horizon, the quantum foam is thought to become exceptionally active. Each pair of virtual particles that flickers into existence here is caught in an extreme gravitational tug-of-war. Normally, these pairs annihilate each other almost instantly. But at the horizon, one particle can fall inward while the other escapes as a faint whisper of radiation, slowly stealing the black hole's mass. This is Hawking radiation. The paradox is that this escaping radiation appears to be completely random, carrying no information about what fell in. The original information about a star, a planet, or a book seems to be scrambled beyond recovery. But what if the information is not lost inside the black hole? What if it is never actually allowed to cross the horizon in the first place? The quantum foam could act as a cosmic scrambler, encoding the information of infalling matter directly onto the fabric of the event horizon itself. Each tiny fluctuation in the foam, each Planck scale bubble, could store a single bit of information, like a pixel on a vast, spherical hard drive. The information is not destroyed. It is holographically plastered across the surface of the black hole, and then slowly leaked back out into the universe imprinted on the Hawking radiation. This idea saves quantum mechanics, but it creates another terrifying problem known as the firewall paradox. If the quantum foam at the horizon is actively processing information, it cannot also be the smooth, empty space that general relativity predicts. The event horizon would be a searing wall of high-energy particles, a firewall that would instantly incinerate anything trying to cross. This is where the specific nature of the foam becomes critical. A highly structured foam, like the spin networks of loop quantum gravity, might offer a way out. In this picture, the foam is not a chaotic storm of energy, but a delicate, woven tapestry. As information approaches the horizon, it is gently woven into the fabric of this spin network, transferred without the need for a violent, energetic firewall. The horizon remains a quantum region, but it is not a deadly one. It is a transformational surface where matter is translated into information, a process mediated by the foam's discrete geometry. This suggests that the paradoxes we face are not failures of our theories, but clues that we are missing the true, foamy nature of reality. The fate of information is tied to the texture of spacetime, and black holes are not cosmic shredders, but the ultimate libraries, their secrets written in the quantum code of the foam. Even light itself cannot escape the subtle texture of the quantum foam. The very fabric of spacetime, if it is a churning sea of microscopic bubbles, should impose a tiny, chaotic friction on anything moving through it. This leads to a startling prediction for the most constant thing in the universe, the speed of light. According to this idea, Light should not always travel at exactly the same speed. For photons with extremely high energy, their journey across the cosmos would be slightly scrambled. The foam's lumpy structure would interact with these energetic particles, causing minute delays and advances. Two photons emitted at the same instant from a cataclysmic event billions of light-years away might not arrive at our telescopes at the same time. The higher energy photon, probing a smaller scale of reality, would stumble through the foam's graininess more noticeably than its lower energy counterpart. It would be like two runners on different tracks, one smooth asphalt and the other a rocky, uneven trail. The runner on the rough path, despite running just as hard, would arrive slightly later. Astronomers have turned to the most violent and distant events in the universe to test this gamma-ray bursts. These are colossal stellar explosions, visible from across the cosmos, that flood space with light of all different energies. By meticulously analyzing the arrival times of these photons after their multi-billion-year journey, scientists can hunt for the fingerprint of the foam. They look for a telltale spread in the arrival times that grows with the distance traveled and the energy of the photon, a delay that cannot be explained by any other known physics. The results, however, have been profoundly puzzling. So far, they have found nothing, no significant delay, no spreading of arrival times that points to a frothy spacetime. The light from these ancient explosions arrives with a synchrony that defies the expectation of a wildly chaotic foam. This null result is not a failure, it is a crucial clue. It tells us that if the quantum foam exists, its structure must be far smoother and more subtle than the most violent models predicted. The foam's grain must be finer than 1/10,000th of a billionth of a billionth of a billionth of a meter, a scale so infinitesimal it pushes the foam into a realm of incredible tranquility. Or perhaps the foam operates by a different set of rules entirely, one where its fluctuations do not disrupt the paths of photons in a simple, random way. The serene journey of light from the edge of the observable universe suggests that the foundation of reality, however quantum it may be, is built with a deep and underlying order. Perhaps the foam is not a feature of empty space, but a sea of forgotten particles. A compelling speculation suggests that what we interpret as the quantum foam is actually a dense, universal background of low-energy neutrinos. These ghostly particles, produced in unimaginable numbers during the Big Bang, flood every cubic centimeter of the universe, trillions passing through your body every second without a trace. Normally, they interact with almost nothing, but at the most fundamental scales, their sheer density could create a turbulent, grainy texture. This neutrino sea would not be a smooth fluid, but a frothing statistical reality, its constant, faint interactions generating the appearance of a fluctuating vacuum. This idea elegantly connects two great mysteries, the nature of the quantum foam and the puzzling properties of neutrinos themselves. We know neutrinos have a tiny, non-zero mass, a discovery that shattered the standard model of particle physics. If they form this primordial background, their collective mass and constant, weak interactions could be the source of the foam's energy and its subtle gravitational effects. This could even provide a new candidate for dark matter, not as a single, undiscovered particle, but as the cumulative gravitational pull of this ancient, ubiquitous neutrino fog. The foam would then be a fossil, a snapshot of the universe's first second, frozen in time and permeating all of reality. We are, in a very real sense, swimming through the faint quantum echo of creation. The serene journey of light from distant galaxies suggests a spacetime smoother than we ever anticipated. But what if its apparent tranquility hides a deeper, more fundamental kind of fuzziness? Another profound theory reimagines the very coordinates of reality, proposing that at the Planck scale, the familiar dimensions of space cease to commute. This is the world of non-commutative geometry. In our everyday world, the order in which you do things does not always matter. Driving 5 miles north and then 5 miles east gets you to the exact same location as driving 5 miles east and then 5 miles north. The operations commute, but in the quantum realm, this is often not true. The act of measuring a particle's position first and its momentum second gives a different result than measuring its momentum first and its position second. Non-commutative geometry applies this quantum principle directly to the coordinates of spacetime itself. It suggests that the very concepts of here and there, of before and after, become blurred at the most fundamental level. You cannot precisely say that one event is to the left of another, because the act of measuring its left-right position interferes with measuring its up-down position. The geometry of space itself becomes inherently uncertain, a fuzzy, foamy landscape where exact locations are a mathematical impossibility. This is not just a turbulent sea of bubbles, but a reality where the map itself has no precise points, only overlapping probabilistic regions. This mathematical framework naturally builds the foam into the equations of the universe. The foam is not an add-on or a side effect. It is a direct consequence of space and time losing their classical, commutative properties. The fabric of reality is woven from a material that is intrinsically blurry. This leads to a specific, testable prediction about the nature of light, a modified dispersion relation. In standard physics, all light, regardless of its color or energy, travels at the same constant speed in a vacuum. But in a non-commutative spacetime, this perfect harmony could be broken. The fuzzy geometry would interact with photons differently based on their energy. A high-energy gamma-ray photon, sensitive to the tiniest ripples in the foam, might travel on a slightly different, more convoluted path than a low-energy radio wave. They would still both travel at the speed of light, but the effective speed through the foamy medium could differ. It would be like two different types of sound waves moving through a complex material, one frequency encountering more resistance than another. This would cause a very specific, cumulative delay in the arrival times of high-energy photons from events like gamma-ray bursts, a signature that physicists are actively searching for in data from telescopes like the Fermi Gamma-Ray Space Telescope. Finding such a signature would be direct evidence that we are living in a universe where the very coordinates of existence are written in a language of quantum uncertainty. This profound blurriness at the foundation of reality forces a monumental question. How does the chaotic, probabilistic dance of the quantum foam give rise to the solid, predictable world we experience every day? The transition from the quantum weirdness of the foam to the reassuring certainty of classical physics is called the emergence of classicality, and its most compelling explanation is a process known as decoherence. Think of the quantum foam as a perfectly still pond. If you drop a single pebble into its center, you create a clean, expanding ripple, a pure quantum state. This ripple represents all the possible positions and states of a particle at once, a superposition. Now imagine that same pond is being constantly pelted by a light drizzle of rain. Each raindrop creates its own tiny ripple, and soon the entire surface is a mess of interfering waves. The clean, single ripple from your pebble is lost in the chaos, its identity washed out by countless tiny interactions. This rain is the environment. Every particle in the universe is constantly being bombarded by photons from the cosmic microwave background, by stray atoms in the air, by the faint gravitational pull of distant stars. These interactions are the raindrops. They force the quantum system to constantly announce its state to the world, and in doing so, they destroy its ability to exist in multiple states at once. The superposition collapses, not because anyone is looking at it, but because the universe is always, unavoidably looking. The foam's wild fluctuations are still there, but for any object larger than a few atoms, they are instantaneously averaged out by this relentless environmental monitoring. Your chair is solid, and in one place because it is being continuously measured by trillions of environmental particles every second, pinning its location down through sheer statistical force. So where in the universe could this delicate quantum coherence possibly survive? The answer is in the most perfect isolation we can find. Deep underground, in laboratories shielded from cosmic rays and background radiation, physicists can trap individual atoms and cool them to near absolute zero. In this pristine silence, far from the environmental rain, quantum superpositions can persist for remarkably long times. The foam's true nature might be glimpsed in the frigid, silent voids between galaxies, or perhaps in the absolute emptiness at the heart of a black hole, where no light or matter can interact to cause decoherence. These would be the last wild places of the universe, where the quantum foam still churns, naked and unobserved, a permanent reminder of the chaotic reality beneath our feet. Long before the first stars ignited, the universe was a seething ocean of quantum foam, its violent fluctuations rippling through the very fabric of newborn spacetime. These primordial tremors may have left behind a permanent echo, a faint hum of gravitational waves that still permeates the cosmos today. This is the stochastic background, a random sea of ripples in spacetime predicted to come from countless sources across the universe. While some waves are generated by colossal events like black hole mergers, a portion of this background could be far more ancient, a direct fossil of the quantum foam's furious activity in the first fleeting moments after the Big Bang. As the infant universe expanded and cooled, the foam's microscopic bubbles did not just vanish. Their frantic churning, the constant warping and unwarping of spacetime itself, could have collectively generated gravitational waves with a unique signature. Unlike the distinct chirp from a single black hole collision, this signal would be a cacophony, a hiss of countless overlapping waves from every direction, carrying with it the raw data of quantum gravity. Detecting this specific hum would be like listening to the universe's birth cry. To hear it, we need observatories of unprecedented sensitivity, operating far from the seismic noise of Earth. The Laser Interferometer Space Antenna, or LISA, is such a mission, planned as a trio of spacecraft flying in a vast triangular formation millions of kilometers apart. LISA will use laser beams to measure the infinitesimal stretching of space caused by passing gravitational waves. It will open a low-frequency window on the cosmos, a realm where the primordial background from the quantum foam is expected to resonate. If LISA or a similar observatory detects this specific stochastic signal, it will do more than just confirm a theory. The precise frequency and amplitude of these waves would act as a cosmic fingerprint, revealing the exact properties of the quantum foam when the universe was less than a second old. Was the foam a chaotic storm or a more structured geometric substance? Did it behave according to the predictions of string theory or loop quantum gravity? The answers would be encoded in those ancient ripples, offering us our first direct look at the quantum architecture of reality itself. This would not just be a discovery, it would be a journey back to the very beginning, allowing us to witness the moment when the foam began to crystallize into the universe we know. The mathematical heart of this vacuum catastrophe lies in a powerful trick called renormalization. It is the tool physicists use to tame the infinities that routinely plague their equations. The process is a bit like a magician pulling an endless string of scarves from a hat, but then cleverly tucking most of them back in before the audience notices. In quantum field theory, you can calculate the absurdly large contribution of the quantum foam's energy, a number that goes off to infinity. Renormalization allows you to subtract this infinity in a controlled way, redefining your starting point so that the final, measurable answer comes out perfectly finite and incredibly accurate. This trick works flawlessly for the electromagnetic force, the weak force, and the strong force, producing predictions that match experiment to an astonishing degree of precision. But when you try to apply it to gravity, the magic fails completely. Gravity, as described by Einstein's general relativity, is not just another force in the universe. It is the geometry of spacetime itself. The energy of the quantum foam, by its very nature, warps this geometry. You cannot simply subtract this infinite warping away, because the stage itself is what is being distorted. It is the difference between having messy actors on a stable stage and having the stage itself melting and buckling beneath their feet. Renormalization can clean up the actors, but it cannot fix a collapsing stage. This is the fundamental incompatibility that has blocked a theory of quantum gravity for decades. Some physicists propose a hidden symmetry so perfect it would force the vacuum energy to be exactly zero. Supersymmetry, for instance, predicts that for every known particle of matter, there exists a superparticle of force, and vice versa. The positive energy contributions from the matter particles would be perfectly canceled out by the negative energy contributions from their force partners. The universe would be in a state of perfect balance, a cosmic zero. The problem is, this symmetry, if it exists, is broken. We do not see these superparticles in our colliders, which means the cancellation is not perfect. It leaves behind a tiny remainder, but that remainder is still dozens of orders of magnitude too large to match our observations of dark energy. The cancellation is like a billionaire losing a penny. The difference is negligible to them, but for our universe, that lost penny is still a mountain of gold. Another, more radical idea sidesteps the calculation entirely. The multiverse theory suggests that our cosmos is just one bubble in an infinite froth of universes, each with its own unique laws and physical constants. In the vast majority of these universes, the vacuum energy is indeed colossal, dooming them to instant expansion or collapse. But by pure statistical chance, a few universes, like our own, ended up with a cosmological constant that is tiny, but not quite zero. In this view, there is no deep reason why our vacuum energy is so small. We simply live in one of the rare, habitable pockets where the numbers accidentally worked out, allowing galaxies, stars, and life to form. We are the cosmic lottery winners, living in a universe whose vacuum energy is just quiet enough to allow for our existence. This anthropic selection effect is a philosophical departure from the quest for a fundamental explanation. It suggests the answer is not found in a single, elegant equation, but in the sheer, mind-numbing statistics of an infinite reality. The foam's energy is not tamed by mathematics, but by the silent, ruthless filter of possibility. The foam's chaotic structure might be threaded with countless invisible tunnels. Deep within the quantum foam, the violent fluctuations could be constantly birthing and destroying the tiniest conceivable wormholes, known as Einstein-Rosen bridges. These are not the stargates of science fiction, but theoretical structures permitted by Einstein's equations, forming a fleeting microscopic web connecting disparate points in spacetime. For decades, they were considered a mathematical curiosity, too unstable to be of any real use, but a revolutionary idea has connected them to one of the most baffling phenomena in physics: quantum entanglement. This is the ER equals EPR conjecture. It proposes that two particles which are mysteriously entangled, their fates linked instantaneously across any distance, are not communicating faster than light. Instead, they are connected by one of these microscopic wormholes woven from the quantum foam itself. The acronym ER stands for Einstein and Rosen, the physicists who first described the wormhole bridge. EPR stands for Einstein, Podolsky, and Rosen, who first highlighted the bizarre implications of quantum entanglement. The conjecture brilliantly unites their two separate puzzles into a single geometric solution. In this view, the spooky action at a distance that so troubled Einstein is not spooky at all. It is a physical connection, a shortcut through the foamy fabric of spacetime. When you create a pair of entangled particles, you are not just linking their quantum states. You are literally pinching the fabric of reality to form a tiny, Planck-scale wormhole between them. This wormhole is not a tunnel through ordinary space you could travel through. It is a tunnel through the geometry of spacetime itself, a direct link that makes the particles effectively adjacent, no matter how far apart they appear in our three-dimensional view. This provides a stunningly elegant picture of how quantum mechanics and gravity might finally be reconciled. The strange, probabilistic rules governing entangled particles could emerge from the dynamical geometry of these microscopic bridges within the foam. When you measure one particle and its state collapses, you are not sending a signal. You are altering the geometry of the wormhole, an effect that is immediately felt by its partner because they share the same spacetime structure. It turns the abstract mathematics of quantum theory into a tangible, physical reality made from the very fabric of the universe. The foam is not just a sea of random bubbles, but a dense, evolving network of connections. And entanglement is the visible evidence of that hidden architecture. Reality may have fewer dimensions than we perceive. At the grand scales of galaxies and planets, we experience a universe of 4 dimensions, 3 of space and 1 of time. But as we plunge deeper into the quantum foam, this familiar structure begins to unravel. In the violent churn of the Planck scale, some theories suggest that spacetime itself undergoes a profound simplification, shedding dimensions like layers of an onion until only 2 remain. This process is called dynamical dimensional reduction. It is as if the intricate tapestry of our 4-dimensional world, when examined under an impossibly powerful microscope, resolves into a far simpler, more fundamental fabric. The extra dimensions do not vanish into nothing. They simply cease to be relevant to the physics at that scale. The wild, fractal nature of the quantum foam at these tiny distances makes the very concepts of length and volume lose their classical meaning. A path between 2 points in this foamy realm is not a smooth line, but a chaotic, crinkled mess that effectively behaves as if it has only 2 dimensions. This is not just a mathematical oddity. It is a potential solution to one of the most stubborn problems in all of physics. The infinities that plague attempts to quantize gravity arise because the force grows infinitely strong at infinitesimally small distances. But if those tiny distances do not exist in the way we think, if the geometry of spacetime becomes effectively 2-dimensional at the highest energies, then the path to an infinite result is cut off. The theory becomes ultraviolet finite, meaning it remains well-behaved and predictable even at the most extreme scales. The foam's chaotic nature provides its own regulator, a built-in safety mechanism that prevents the mathematics from blowing up. How could we ever test such a bizarre idea? The key might lie in the very fabric of the cosmos. The early universe was a place of unimaginably high energy and tiny size, a domain where this two-dimensional physics would have reigned supreme. As the cosmos expanded and cooled, it underwent a phase transition, crystallizing into the four-dimensional reality we know today. The afterglow of the Big Bang, the cosmic microwave background, might still carry faint imprints of that primordial, lower-dimensional state. Furthermore, if high-energy particles from distant gamma-ray bursts are interacting with a spacetime that has a fractal, dimensionally reduced structure, their journey across the universe could carry a unique signature, a subtle scrambling of their arrival times that differs from the predictions of other foam models. Finding that signature would be like discovering the ghost of a simpler universe, a permanent whisper in the foam that tells us our complex reality is just an emergent illusion. Gravity feels so weak because it is spread across a hidden landscape woven in the quantum foam. This is the heart of the hierarchy problem, a puzzle that asks why gravity is so unimaginably feeble compared to the other fundamental forces. The electromagnetic force that holds atoms together is stronger than gravity by a factor of 1 followed by 36 zeros. To feel the difference, just lift a paperclip with a small magnet. That tiny magnet effortlessly defeats the gravitational pull of the entire planet Earth. This disparity is not just a curiosity, it points to a deep crack in our understanding of physics. The energy scale where gravity becomes as strong as the other forces, the Planck scale, is 1,000,000,000,000 times more energetic than the scale we can probe with our largest particle colliders. This gap is the hierarchy, and the quantum foam may be the key to understanding it. One compelling theory suggests the foam's structure itself acts as a natural damper on gravity's strength. In the seething chaos of the Planck scale, gravity is in its element, a powerful force interacting directly with the foam's turbulent geometry. But as we move to our larger, calmer world, this intense interaction is averaged out. The foam's microscopic twists and turns effectively dilute gravity's influence, making it appear weak on our human scale. It is not that gravity is inherently weak, but that we are seeing its echo after it has been scrambled by the foam's chaotic texture. An even more radical solution involves the very shape of reality. Our universe might be a three-dimensional membrane, or brain, floating within a higher dimensional expanse. The other forces, like electromagnetism, are stuck to our brain, their influence confined to our slice of reality. But gravity, born from the geometry of spacetime itself, can leak off our brain and into the bulk of these extra dimensions. It dissipates into the quantum foam of a larger, hidden cosmos. We only feel a tiny fraction of its true strength, like hearing a loud concert from outside a thick-walled building. The music seems faint to us, not because the band is quiet, but because most of the sound is trapped inside. In this picture, the immense gap between gravity and the other forces is an illusion of our perspective. At the Planck scale, deep within the foam, all forces are unified and equally potent. We simply live in a quiet backwater, a sheltered corner of a much wilder, higher dimensional universe where gravity has room to roam. This elegant idea transforms the hierarchy from a problem into a clue, a direct hint that the quantum foam is not an empty void, but a vast, structured landscape with hidden depths we have only begun to explore. The quantum foam might be warm. It has long been considered the fundamental ground state of reality, the baseline of absolute zero from which everything else emerges. But a provocative theory suggests this is wrong. The foam could be a thermal state, possessing a very low but real temperature, humming with a faint heat born from its own restless activity. This is not a temperature we can feel, but one that could be imprinted on the fabric of spacetime itself. If true, it means the vacuum of space is not cold and dead, but subtly warm with quantum energy. This idea connects directly to one of the most startling predictions in modern physics, the Unruh effect. According to this, an observer accelerating through what seems like empty space will not see a vacuum. They will instead find themselves immersed in a warm bath of radiation. The harder they accelerate, the hotter this thermal glow becomes. For someone accelerating at a tremendous rate, the void would shine as brightly as a furnace. This is not a mere illusion. The radiation is real, a consequence of the quantum fields being dragged along by the accelerating motion. Now, apply this concept to the quantum foam. Each microscopic bubble in the foam is a region of incredible fluctuation, a point where spacetime is churning with virtual energy. This frantic motion could be seen as a form of inherent, chaotic acceleration across the Planck scale. If every point in the foam is, in a sense, accelerating, then every point should be generating its own tiny bit of Unruh radiation. The foam would be a seething thermal tapestry, glowing with a universe-wide heat. This leads to an even more incredible possibility. Just as a black hole is predicted to slowly evaporate by emitting Hawking radiation, the quantum foam itself might be doing the same. The intense, warped regions around each Planck scale bubble could act as microscopic event horizons, each one leaking a faint whisper of thermal energy. We would not see this as a flash of light, but as a pervasive, impossibly faint background hum of radiation woven into the vacuum. Detecting it would be the ultimate challenge, like trying to hear the sound of individual snowflakes landing in a blizzard. Yet if we could, it would confirm that the foam is not the bottom level of reality, but a state in thermal equilibrium, a simmering sea with its own temperature and thermodynamics. This would force us to rewrite our understanding of nothingness, revealing a vacuum that is alive with a deep, residual warmth, the last embers of creation's first fire. Perhaps the most intimate mystery of the quantum world is the measurement problem. Why does a particle exist in a blurry cloud of possibilities until the moment we observe it, when it suddenly snaps into a single, definite reality? This transition from the quantum to the classical, the collapse of the wave function, has baffled physicists for a century. But what if the trigger for this collapse is not our conscious observation, but something far more fundamental, the quantum foam itself? This idea forms the basis of objective collapse models, which propose that the wave function is inherently unstable. It cannot maintain its delicate superposition forever and will spontaneously collapse after a certain amount of time. The quantum foam, with its constant, seething fluctuations in spacetime, provides the perfect mechanism for this. Each tiny bubble in the foam is a minuscule gravitational tremor, a jitter in the very stage upon which particles perform their quantum dance. For a large object like a chair, these tremors are irrelevant, averaged out into nothingness by its trillions upon trillions of atoms. But for a single, isolated electron in a superposition, each individual tremor is a significant event. The relentless pounding from the foam's chaotic energy constantly nudges the particle, forcing it to choose a state. In this view, collapse is not a mystery, it is an inevitable physical process, like a pencil balanced on its tip, eventually falling over due to random vibrations in the air. The foam is that random vibration for the entire universe. This elegantly explains why large objects are never seen in quantum superpositions. Their wave functions collapse almost instantly under the sheer volume of interactions with the foam. However, this idea faces a significant challenge. If the foam is constantly collapsing quantum states, it should also be producing a faint, universal background of radiation, a whisper of energy released every time a wave function falls into a definite state. This is an effect we have not yet detected with our most sensitive instruments. The search for this signal is ongoing, pushing our technology to its limits to hear the faint crackle of reality constantly resolving itself. If such a model is correct, it paints a stunning picture. There is no separate classical world and quantum world. There is only one reality, built upon a churning gravitational foam that constantly measures itself into existence. We are not outside observers causing collapse. We are part of the foam's endless, self-measuring process, living in a universe that is forever deciding what it is. Our entire observable universe could be the product of a single, exceptionally rare bubble in the quantum foam. In the first fleeting fraction of a second after the Big Bang, the cosmos was a seething, hot plasma where the forces of nature were unified. But as it expanded and cooled, it underwent a series of phase transitions, much like steam condensing into water. The quantum foam during this epoch was not a calm sea. It was a cauldron of boiling spacetime, with bubbles of different vacuum states constantly forming and collapsing. Most of these bubbles were tiny and ephemeral, vanishing almost as soon as they appeared. But according to some models of cosmic inflation, one of these bubbles was different. A patch of spacetime, through a colossal and incredibly rare quantum fluctuation, found itself trapped in a state of false vacuum, a high-energy configuration that was metastable. This patch was like a bubble of superheated water in a pot that refuses to boil, possessing a tremendous negative pressure. And in the strange physics of general relativity, negative pressure generates a powerful repulsive force. This one lucky bubble from the foam did not collapse. Instead, it began to inflate at an exponential rate, doubling in size over and over again in an unimaginably short time. In less than a blink of an eye, that sub-microscopic patch of foamy spacetime expanded to a size larger than our entire visible universe today. Everything we see, every galaxy, every star, every planet, was once contained within that single quantum fluctuation. This explains the remarkable uniformity of the cosmos, the fact that the temperature of the cosmic microwave background is almost exactly the same in opposite directions. Those distant regions were once in causal contact, knitted together before inflation blew them apart. But the story does not end with smoothness. The quantum foam did not just provide the seed for inflation, it also gave our universe its rich structure. Even during the inflationary phase, the foam was still churning at the smallest scales. Its relentless fluctuations, these tiny tremors in spacetime, were stretched to astronomical sizes by the incredible expansion. Imagine a tiny, wrinkled piece of plastic being blown up into a gigantic balloon. The minute wrinkles become vast mountains and valleys. In exactly the same way, the microscopic ripples in the quantum foam were magnified into faint variations in the density of matter and energy across the cosmos. These primordial density perturbations are the blueprints for all structure. The slightly denser regions, imprinted by the foam's own texture, had a bit more gravitational pull. Over billions of years, they attracted more and more matter, eventually collapsing into the first stars, and the great cosmic webs of galaxies we observe today. We can see the direct evidence for this when we look at the cosmic microwave background, the afterglow of the Big Bang, the tiny temperature variations, those hot and cold spots mapped so precisely by satellites like Planck, are not random noise. They are a fossilized imprint, a baby picture of the quantum foam itself, magnified to cover the entire sky. The largest structures in the universe were born from the smallest possible vibrations in the fabric of reality. That same foam could be the reason black holes are the most efficient information storage devices in the universe. When Jacob Bekenstein first proposed that a black hole's entropy is proportional to the area of its event horizon, it was a radical departure from all known physics. Entropy is a measure of disorder, the number of ways a system's microscopic components can be arranged while still looking the same from the outside. For a hot gas, entropy is related to its volume. But Bekenstein claimed that for a black hole, the ultimate sink of matter and energy, the entropy is tied to its surface area. Stephen Hawking initially resisted the idea, but his own work on Hawking radiation confirmed it, leading to the famous formula S equals A divided by 4. The letter S stands for entropy, and A is the area of the event horizon in Planck units. This equation is deceptively simple. It tells us that every single square Planck area on a black hole's surface, that unimaginably small patch of space, can hold exactly 1/4 of a single bit of information. But what are the microscopic components that this entropy is counting? What are the individual parts being shuffled around to create this immense disorder? The leading candidate is the quantum foam. The event horizon is not a smooth, featureless membrane. According to this theory, it is a seething layer of Planck-scale fluctuations, a turbulent foam where spacetime is constantly twisting into tiny virtual black holes and wormholes, bubbling and fizzing with incredible activity. Each one of these foam bubbles represents a single microscopic degree of freedom, a fundamental unit that can be in one of a few possible states, like a switch that can be on or off. The Bekenstein-Hawking entropy is then a count of all the possible ways this entire foamy landscape can be configured. Imagine the event horizon as a vast chessboard, but with an astronomically large number of squares. Each square is a single Planck area, and on it sits a component of the foam that can vibrate or twist in a handful of distinct ways. The number of possible arrangements of all these tiny twists and vibrations is the entropy of the black hole. The formula S equals I over 4 is the breathtakingly simple result of counting them all up. This gives us a profound insight into the nature of reality. It suggests that information is not stored within the volume of the black hole, but is painted onto its surface, one binary bit for every 4 Planck areas. The three-dimensional interior, with all the stars and planets that fell in, is somehow encoded on a two-dimensional boundary. The quantum foam is the physical medium for this cosmic hard drive. Its endless churn is not random noise, but the sound of information being processed and stored at the most fundamental level of spacetime. The event horizon is not a wall of death, but the most densely packed library in existence, its secrets written in the frenzied, foamy script of quantum gravity. The foam's faint tremors may be too subtle for light, but they could leave a mark on matter itself. Scientists are now turning to some of the most precise instruments ever built, atom interferometers, to feel for the space-time jitter that photons seem to ignore. These devices exploit the quantum wave nature of atoms, using lasers to split a single atom's wave function into 2 separate paths that travel through space before recombining. In a perfectly smooth, classical spacetime, The two paths would reunite to create a predictable interference pattern, like two sets of ripples in a pond merging perfectly. But if the quantum foam is real, the path of each atom would be randomly jostled by the foam's turbulent geometry. This microscopic buffeting would cause a slight stochastic shift in the interference pattern, a telltale blurring that betrays the foam's presence. The level of precision required is almost beyond comprehension. These experiments must detect a potential shift in the atom's position on the scale of a single Planck length, a distance so minuscule that it is to a meter what a single atom is to the entire observable universe. To achieve this, the experiments are conducted in ultra-high vacuum chambers, shielded from every conceivable vibration, magnetic field, and electrical influence. The atoms are cooled to temperatures just a whisper above absolute zero, rendering them almost perfectly still to isolate the faint signal of spacetime itself quivering beneath them. A positive result, the clear detection of this atomic jitter, would be a revolutionary moment. It would directly validate that spacetime is indeed granular, providing the first experimental evidence for a theory of quantum gravity. The specific character of the detected noise could then be analyzed like a fingerprint, potentially ruling out some models, like highly chaotic foams, while supporting others, like the more structured spin networks of loop quantum gravity. It would tell us that the universe is fundamentally pixelated. A negative result, however, the continued, serene silence of the atoms, would be equally profound. It would force theorists to reconsider the most violent models of the foam, suggesting that spacetime's quantum structure is far more ordered and tranquil than anyone predicted, perhaps pointing toward the smooth emergence seen in causal dynamical triangulations. Either way, the outcome pushes our understanding of reality to its absolute limit, using the quiet fall of a single atom to listen for the faint, churning heartbeat of the cosmos. Deep in the silent expanse of the solar system, two robotic pioneers drifted toward the stars, each carrying a secret. As the Pioneer 10 and 11 spacecraft journeyed beyond the orbit of Pluto, scientists tracking their trajectories noticed something deeply puzzling. Both probes were experiencing a tiny, constant, and unexplained deceleration back toward the sun. A deviation so slight it was barely measurable, yet it was undeniably there. This was the Pioneer anomaly, a ghost in the machine of deep space navigation. For years, it defied all conventional explanations, from the gentle push of leaking propellant to the subtle thermal radiation from their nuclear power sources. When every ordinary cause was exhausted, a few theorists looked to the extraordinary. They proposed that the probes might not be slowing down at all from our perspective, but that the very fabric of space through which they traveled was subtly different than expected. Perhaps the quantum foam, that churning substrate of reality, was not perfectly uniform. What if the probes were moving through a region where the foam's texture imparted a faint, additional drag, a minuscule friction against the geometry of spacetime itself? It would be like a ship sailing through water of a slightly different density, its speed imperceptibly altered by the medium. This idea was thrilling because it suggested a way to finally detect the foam's influence not with light, but with the physical motion of a human-made object. A spacecraft could act as a plumb line, dragging through the quantum depths and feeling a tug that our telescopes could never see. For a brief, exciting period, the Pioneer anomaly was a beacon of hope for quantum gravity researchers. Yet, like so many ghosts, this one eventually faded. Meticulous, years-long analysis finally pinpointed the most likely culprit, a previously underestimated effect from the spacecraft's own heat. The gentle infrared radiation emitted by the onboard power sources was acting like a tiny, weak photon rocket, pushing back against the direction of travel with just enough force to account for the anomaly. The case was largely closed, the exotic explanations set aside, but the lesson of the Pioneer anomaly remains profoundly important. It teaches us about the immense challenge of detecting the quantum foam. Its effects, if they exist at all, are so infinitesimally small that they are drowned out by the most mundane of physical processes, the simple physics of heat and light. To find the foam's signature, we must build experiments of such exquisite precision that they can isolate a whisper from the quantum realm from the roaring background noise of the classical universe. The Pioneer's silent journey showed us just how quiet we must learn to be. The universe might not merely contain computers, it could be one. Another breathtaking theory suggests the quantum foam is not just a seething structure, but the ultimate computational substrate, a cosmic processor running the ultimate simulation, reality itself. This idea, known as pancomputationalism, proposes that every fluctuation in the foam, every microscopic bubble of spacetime, is not a random event. It is a fundamental operation, a single logic gate in a calculation of cosmic scale. Each time a virtual particle pair flickers into existence, it is not just a quantum fluctuation, it is a bit being flipped. Every reconnection in a spin foam is a logical operation. The entire churning, turbulent history of the cosmos could be the output of this relentless, underlying computation. Think of a modern computer chip, with its billions of transistors switching on and off to create the rich, complex world of a video game. The quantum foam would be the universe's version of that chip, but with its transistors woven from the fabric of spacetime. The laws of physics, from the elegant dance of gravity to the strict rules of quantum mechanics, would not be fundamental laws at all. They would be the emergent software, the high-level programming language that arises from the foam's relentless, bottom-level processing. This leads to a staggering question. If the universe is a computer, what is it calculating? The answer might be the simplest and most profound of all. It is calculating itself. Every moment, every interaction, from the fusion of atoms in a star to the firing of a neuron in your brain, is part of the ongoing computation whose output is the present state of everything that exists. The arrow of time is simply the direction in which this computation is running. This reframes the very nature of existence. We are not just living in a universe that can be described by mathematics. We are living inside a mathematical process, a dynamic, evolving computation. The quantum foam is the hardware, and the unfolding story of the cosmos is the data being processed. It suggests a deep connection between information, matter, and energy, not as separate things, but as different manifestations of the same fundamental computational reality. The search for a theory of quantum gravity then becomes a search for the universe's operating system, the foundational code that governs how spacetime itself processes information. Are we and everything we perceive simply the beautiful, intricate output of a program running on the quantum foam of a cosmos that is not just built like a computer, but is one? Could our own consciousness be a direct window into the quantum foam? This is the extraordinary claim of a theory known as orchestrated objective reduction, or ORCH. It proposes that the seat of our awareness is not simply the brain as a whole, but structures inside our neurons called microtubules. These tiny protein cylinders are not just cellular scaffolding. According to this theory, they are quantum computers, where electrons can exist in a state of superposition, humming with multiple possibilities simultaneously. The theory then makes a breathtaking leap, suggesting that this delicate quantum coherence is not destroyed by the noisy environment of the brain. Instead, it is protected, and its eventual collapse is not random. It is orchestrated by the very fabric of reality. The quantum foam, with its fundamental fluctuations in spacetime geometry, is what ultimately reaches in and orchestrates the collapse of these quantum states in the microtubules. Each collapse is a moment of definite reality, a single frame in the film of our conscious experience. In this view, thinking and feeling are not just chemical processes. They are a dynamic dance with the deepest level of spacetime. Consciousness is not computed by the brain. It is the universe itself, through its foamy foundation, becoming aware of itself. This idea, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, is as controversial as it is profound. The scientific criticism is fierce. Most physicists argue that the warm, wet environment of the brain would cause decoherence in a fraction of a nanosecond, far too quickly for any meaningful quantum computation to occur. It would be like trying to perform a complex calculation on a computer submerged in a raging hurricane. The brain, they say, is the last place you would find such delicate quantum states. Proponents counter that the unique structure of the microtubules, with their ordered water and protective mechanisms, could create pockets of isolation where quantum coherence can persist. The philosophical implications are even more staggering. If Or is correct, then consciousness is not an emergent property of complex computation, but a fundamental feature of the universe, as basic as space and time. It suggests a cosmos where mind and matter are inextricably linked at the Planck scale. And our inner world of thoughts and feelings is a direct resonance with the churning quantum sea from which all reality is born. Whether this theory is a brilliant insight or a beautiful dead end, it forces us to confront the most intimate mystery of all. Is the foam not just the fabric of space, but the substance of the self? Our most detailed map of the early universe might be built upon a paradox. The cosmic microwave background, that ancient light from the dawn of time, carries faint ripples that are the blueprints for all cosmic structure. These ripples were once incredibly small quantum fluctuations, stretched to cosmic size during inflation. But here lies the trans-Planckian problem. To produce the patterns we see today, these fluctuations must have started with wavelengths far, far smaller than the Planck length. This is a profound issue because our current physics breaks down at the Planck scale. It is like saying a skyscraper's design depends on the precise arrangement of individual atoms, but we have no theory for how atoms behave. We are tracing our universe's origin to a regime where our understanding of spacetime completely vanishes. The quantum foam, with its inherent graininess, offers a stunningly simple solution. If spacetime is indeed a foamy structure with a fundamental minimum length, like the Planck length, then there is a natural cutoff. Fluctuations cannot be squeezed infinitely small. The foam acts as a cosmic pixel size, preventing wavelengths from becoming smaller than this fundamental unit. It places a hard limit on how far back we can extrapolate our physics, shielding the early universe from our own ignorance. This does not just solve a theoretical headache, it leaves a potential fingerprint. A foamy cutoff would subtly alter the statistical properties of those primordial ripples. It would change the predicted power spectrum of the cosmic microwave background, particularly on the very largest scales. Our most precise satellite observations, from missions like Planck, are now sensitive enough to hunt for these tiny deviations. Finding a signature of a minimum length in the CMB would be direct observational evidence that the universe is not infinitely divisible, that the quantum foam is real, and that the largest structures we see were born from a reality that is fundamentally pixelated. We have journeyed through 30 different visions of the quantum foam, from a turbulent sea of bubbles to a cosmic superfluid, a holographic projection, and a woven tapestry of loops. This brings us to a final, overarching question. Is the quantum foam itself a genuine stepping stone toward a final theory of everything? Or is it a flawed metaphor that will one day be discarded? The answer depends entirely on which path through theoretical physics ultimately proves correct. Each major approach treats the foam with a different philosophy. String theory smooths it out with vibrating strings and extra dimensions, treating it as a consequence of objects moving within a pre-existing arena. Loop quantum gravity builds spacetime from the foam itself, creating a granular, discrete reality from the bottom up. Causal dynamical triangulations shows how a smooth universe can spontaneously emerge from a chaotic soup of quantum building blocks. And the holographic principle suggests the foam is not even fundamental, but a projection from a distant, two-dimensional surface. The strength of the foam concept is its powerful intuition. It gives us a tangible, physical picture for the Planck scale, a way to conceptualize the marriage of quantum mechanics and gravity. It has generated testable ideas, from modified light speeds to atomic jitter, driving experimental design for decades. Yet its greatest weakness may be this very flexibility. The foam can be modeled as a stormy sea, a calm fluid, a computational grid, or a fuzzy geometry. If a concept can be molded to fit almost any theory, does it still hold concrete meaning? The fate of the quantum foam will not be decided by theoretical elegance alone, but by cold, hard data from the edges of our knowledge. Is the fabric of spacetime truly pixelated? The next generation of experiments holds the key. Atom interferometers listening for the faint jitter of reality, space-based gravitational wave observatories like LISA hunting for the primordial hum of the foam, and ever more precise maps of the cosmic microwave background, searching for the imprint of a fundamental length. These are the tools that will move us from speculation to discovery. A single, clear signal from any one of these endeavors would revolutionize physics, confirming that space-time is indeed granular and forcing every theory to conform to that new reality. Conversely, if experiment after experiment returns only a serene silence, if space-time continues to appear perfectly smoothed down to the finest scales we can probe, then the idea of a chaotic quantum foam may slowly fade, replaced by a new, perhaps even more bizarre, paradigm we have not yet conceived. The quantum foam represents our current frontier, the place where our understanding dissolves into a beautiful, terrifying, and magnificent mystery. Its ultimate truth is still written in the void, waiting for us to learn how to read it. We have ventured across a landscape of 30 possibilities, where the void itself churns with potential. From the faint push of dark energy to the information-devouring paradox of black holes, the quantum foam offers a radical redescription of reality. It redefines time from a fundamental river to an emergent story, and rewrites the cosmos from a smooth stage to a seething digital tapestry. While no experiment has yet captured its direct fingerprint, the very pursuit of this grainy foundation is reshaping physics at its core. It forces us to question the nature of existence, pushing our most powerful theories to their breaking point in the hope of a deeper union. This journey through the foam is far from over. It is the thrilling, ongoing quest to read the first lines of the universe's source code. So we turn this final question to you. Which of these theories resonated most deeply? Did the holographic universe shift your perspective? Or did the idea of a cosmic superfluid change how you see the void? Let us know in the comments. And if you are hungry for more journeys to the edge of understanding, subscribe to keep exploring. The greatest lesson of the quantum foam may be this: reality is always more bizarre, more complex, and more magnificent than our boldest imagination.